This is Mrs. Zappia with Lesson 9, Scientific Notation, from Grade 8, Module 1. Student outcomes for this lesson. Students write, add, and subtract numbers in scientific notation and understand what is meant by the term leading digit. Our essential question is, how do I determine the exponent for 10 when writing a number in scientific notation? Let's go through each vocabulary word and then pause the video to write the definition. Scientific notation is a number expressed as a product of a decimal times a power of 10, where the decimal is a finite decimal, so that the decimal is greater than or equal to 1 and less than 10. And n, the exponent, is an integer, so it can be positive or negative. A negative integer exponent would give us a very small number, and a positive exponent would give us a very large number. The order of magnitude refers to how big or how small a number is. In the term 10 to the nth power, the exponent n determines the order of magnitude. The leading digit is the leftmost digit. For example, in the number 58,420,000, the leading digit is 5. Example 1. How could you check to see if these are indeed equivalent? So the finite decimal, 234 and 567 thousandths, is equal to every one of the following. So what I want you to notice here is that the decimal is changing position and the exponent of the power of 10 is changing. So in the first number we have 2.3467 times 10 to the second power. So what you're doing here is you're actually multiplying by 100. In the next problem, we have 0.234. So notice that the decimal has moved over one place. And our exponent has increased one place, or one place value. So when you multiply by 10 to the third, you are actually multiplying by 1,000. And that's why these are equivalent. Because here your decimal has gotten smaller, but your power of 10 has gotten larger. In the next problem, our decimal has moved over from the 0.23 to 23 point. So here our decimal has gotten larger. When your decimal gets larger by 2 place values, then your exponent must get smaller by 2 place values. So here you're just multiplying by 10. Which is a representation of 234 and 567 thousandths in scientific notation? Remember that scientific notation is a decimal where that decimal has to be greater than or equal to 1 and less than 10. So our first number is the one that is written in scientific notation. How could you check to see if these are indeed equivalent? You could do the multiplication and compare the products. So I would challenge you to pause the video and to take your calculator and multiply some of these out. When you enter these on your calculator, you'll want to make sure that you use your exponent key, such as this. You would enter 2.34567 times 10 to the second power equals. Then when you get down here, you would enter 234.567 times 10 to the 0 power equals. And then it works in the same way for the exponents that are negative. And you need to make sure that you use the negative key but not the subtraction key. So we would enter 234.567 times 10 to the negative 3 equals. And then you can see that all of those products are the same. In example 1b, write each number in scientific notation. Now, this is not in your notes, but I would like you to add it. So scientific notation, remember, is a decimal that is greater than or equal to 1, but less than 10, times a power of 10. What we need to do to find out what this decimal would be is to move the decimal so that it will be after the leading digit. So that will need to be 475. And the leading digit would be 4, so our decimal would have to go after the 4. Then our power of 10 is determined by how many places we move the decimal, and that would be 1, 2, 3, 4 places. and we are moving it to the right, and that will give us a negative 4. When your exponent is negative, notice that it doesn't make your number negative. It just means that you're multiplying by a number that is less than 1. This example, 10 to the negative 4, is actually 1 over 10 to the 4, or you could say 1/10,000th. So this is our number in scientific notation. Now this is a rather large number, so our exponent for the base 10 will be positive. So here we want our decimal to be after the leading digit, which will be 5. Then our power of 10 is determined by how many places we move our decimal. So that's 1, 2, 3, 4, 5, 6, 7, 8. So our exponent is 8. Now I want you to notice that the exponent is not determined by the number of zeros. Rather, it is determined by how many places you had to move your decimal. Here, we would need to multiply our number by 10 to the 8th power in order to get back to the standard notation. On your own, are the following numbers written in scientific notation? If not, state why. Pause the video and do exercises 1 through 6. Resume the video when you're ready. In example 2, let's say we need to determine the difference in populations from Texas to North Dakota. In 2012, Texas had a population of about 26 million people. North Dakota had a population of about 6.9 times 10 to the 4th power. We begin by writing each number in scientific notation. To find the difference, what operation should we use? Well, what I want you to notice is that we have two different forms of a number. We have a standard notation of 26 million and scientific notation. In order to find the difference, they need to be in the same form. Since we're working with scientific notation, we will put them both in scientific notation and then find the difference. Remember that difference means subtraction. In scientific notation, we need our decimal to be after the leading digit, so that will be 2.6 times 10 to the. This is a very large number, so our exponent will be positive. So we need to move it 1, 2, 3, 4, 5, 6, 7 places. So there's our scientific notation for 26 million. North Dakota, our decimal will need to go after the leading digit, so that's going to be 6.9 times 10 to the 1, 2, 3, 4, 4th power. Now we're ready to find the difference. So we have 2.6 times 10 to the 7th power, and we want to subtract 6.9 times 10 to the 4th power. In order to do the subtraction, the order of magnitude must be equal. That is to say, each number must have the same order of magnitude and the same base. Well, the base is the same. We have base 10 for both of those exponents, but the order of magnitude is different. So what we need to do is we need to rewrite one of them so that it matches the other. The easiest way to do this is to use the larger order of magnitude. So here we're going to rewrite this part. And we've got 2.6 times 10 to a power times 10 to a power. And what we need to do is use 10 to the 4th as one of those factors so that we can do the subtraction. We know that according to the product of powers rule that these exponents must add up to 7. So that would make this exponent 3. So all I've done here is I've rewritten 2.6 times 10 to the 7th as 2.6 times 10 to the 4th times 10 to the 3rd. Now what I want to do is I want to preserve 10 to the 4th power so that I can subtract these numbers. So I want this to remain as one of the factors. So that's 10 to the 4th. Then what I do is I multiply these numbers. 10 to the 3rd is 1,000. So 2.6 times 10 to the 3rd is 2,600. A good way to do that, or an easy way to do that, is to look at your exponent of 3 and then just move your decimal 3 places. 1, 2, 3. Fill that in with zeros and you've got 2,600. Now I can subtract because I have the same order of magnitude. Notice that when I rewrote this with a different order of magnitude, that my exponent decreased by 3 place values. When your exponent decreases by 3 place values, then your decimal must increase by 3 place values. Now I'm going to rewrite this using the distributive property. So I have 2600 minus 6.9 times 10 to the fourth. Go ahead and subtract your decimals, and that gives us 2593.1 times 10 to the fourth power. And remember that 10 to the fourth power is 10,000. So at this point, you could answer in two different ways. You could change this to standard notation, or you could write it in scientific notation. We're looking for the difference in population, so we want to answer in standard notation. So I'm going to multiply this by 10 to the fourth. 10 to the fourth is equal to 10,000. So I can either multiply it by 10,000, I can use my calculator, or I can simply move my decimal 4 places. So I'm going to take 25931, and I'm going to move my decimal 4 places. 1, 2, 3, 4. Fill those in with zeros. So I have 25931,000. When you have a large number, you want to make sure that you use commas to make reading the problem easier. This number is 25,931,000, and this is the difference in population between Texas and North Dakota. Write study questions here that will help you to remember the process and reasoning. Remember to add and subtract numbers in scientific notation. Each number must have the same order of magnitude, which is the same exponent, and the same base 10. Example 3. Let's say that we need to find the combined mass of 2 hydrogen atoms and 1 oxygen atom. So we need 2 hydrogen and 1 oxygen. It's normally written as H2O, 2 hydrogens and 1 oxygen, or otherwise known as water. To appreciate the value of scientific notation, the mass of each atom is given in standard notation. So this is the mass of 1 hydrogen atom, and this is the mass of 1 oxygen atom. And we want to find the combined mass. The combined mass means that we want to add those together. So the purpose of this is scientific notation. So we're going to write each one in scientific notation and then add them together. Okay, so we're going to have 2 hydrogen atoms, and we want to write our hydrogen atom in scientific notation. Our decimal needs to go after the leading digit, so it will be 1.7 times 10. Then our power of 10 is going to be negative because this is a very small number. We're moving our decimal to the right. And to determine your number of your exponent, remember it is not the number of zeros, it is rather how many places you have to move the decimal. So these are in groups of 3, so that's going to be 1, 2, 3, 4, 5, 6. I'm just going to count how many groups of 3. 1, 2, 3, 4, 5, 6, 7, 8. Well, 8 groups of 3 is 24. 24, 25, 26, 27. So this is to the negative 27th power. Then let's write our oxygen atom in scientific notation. Our decimal will need to go after the leading digit, so we will need to move it after the 2. So now the leading digit is 2, 2.7, times 10 to the negative. Then determine your exponent. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3 is 24. 25, 26. So this exponent is negative 26. Now we have 2 hydrogen atoms, so we need to multiply 2.2 times 1.7, which is 3.4, times 10 to the negative 27. And you can double check this calculation on your calculator to make sure that it is correct. Minus 2.7 times 10 to the negative 26. In order to do this calculation, your order of magnitude needs to be the same, and it is not right now. So what I want to do is I want to rewrite this number using the same order of magnitude. I'm going to use the larger, which is negative 26. So I'm going to rewrite this product as 3.4 times 10 to the negative 26 times 10 to the... Remember that these two exponents need to add up to negative 27. So negative 26 plus negative 1 equals negative 27. Then I want to preserve this order of magnitude so that I can do the subtraction. So this is the power of 10 that stays, and I multiply 3.4 times 10 to the negative 1. When you change your order of magnitude by one place value on the exponent, you also need to change your decimal by one place value. And so this number will get smaller by one place value. So we have, moving our decimal one place, 0.34 times 10 to the negative 26 minus the quantity 2.7 times 10 to the negative 26. Now that we have the same base 10 and exponent negative 26, we can rewrite this using the distributive property. So we have 0.34 minus 2.7 times the quantity 10 to the negative 26. The subtraction, we have 3.04. Oh, we are adding these together, sorry. We are combining these. Let's go back and change all of these to addition. There we go. So we have a combined mass of 3.04 times 10 to the negative 26th power. Now, in the previous example, we left the number in standard form. And in this example, we are going to leave the number in scientific notation because there are so many zeros. This is such a small number. So we're going to leave that in scientific notation. Could we have solved this problem using a different common order of magnitude? So we've got the original problem, which was 3.4 times 10 to the negative 27 power. Add 2.7 times 10 to the negative 26 power. What they're asking is, could we have changed the exponent to be the common exponent of negative 26 instead of negative 27? No, that's what we did. In the next section, could we have solved this problem by using a different common order of magnitude? In other words, could we have used the common order of magnitude as negative 27 instead of negative 26? Let's try it. Our original problem is 3.4 times 10 to the negative 27 plus 2.7 times 10 to the negative 26. And again, the question is asking, could we use negative 27 instead of negative 26? So what we want to do is we want to rewrite this part of the problem this time. So we want 2.7 times 10 to the negative 27 times 10 to the blank. And the reason we're using 10 to the negative 27 is so that we have a common order of magnitude. Then this missing exponent, these two exponents together need to add to negative 26, and so this must be a positive 1. Then to preserve 10 to the negative 27, we multiply 2.7 times 10 to the first, which is 10, and that gives us 27. So we're rewriting this part of the problem as 27 times 10 to the negative 27. And we're adding that to 3.4 times 10 to the negative 27. Now that we have a common order of magnitude, we can rewrite this problem according to the distributive property as 3.4 plus 27 times 10 to the negative 27th power. Combining your decimals, that gives us 30.4 times 10 to the negative 27. Then you think, does that match what we had before? It does not match, but are they equivalent? Yes, they are. We can change this one to scientific notation so that it matches the above exponent. And we can change the order of magnitude again back to 10 to the negative 26 by moving our decimal one place. And that would give us 3.04 times 10 to the negative 26. So you do get the same answer. The question is, could we have solved this using a different common order of magnitude? And the answer is yes. So when you look at your original problem and you think, which exponent should I change it to, the larger or the smaller, it doesn't matter. You will get the correct answer either way. Changing the order of magnitude. So let's just practice changing the order of magnitude a bit. Here we have go ahead and copy these problems and leave some room in between to solve them. 2.3 times 10 to the 7th. We want to change that order of magnitude to 10 to the 5th. So we are going to rewrite this as 2.3 times 10 to the 5th times 10 to the blank. We want to preserve 10 to the 5th. So that needs to be included in this new product. Then know that your two exponents must add up to 7. So 5 plus 2 is 7. Then, to preserve 10 to the 5th, we multiply 2.3 times 10 squared, which is 100. So that's going to be 230. 230 times 10 to the 5th is equivalent to 2.3 times 10 to the 7th. In our next example, we want to change our order of magnitude to 10 to the 7th. So we rewrite 6.3 times 10 to the 7th times 10 to the blank. We want to preserve 10 to the 7th, so it does need to be included there. Understand that these two exponents need to add up to 5, and that would make this exponent negative 2. Then multiply 6.3 times 10 to the negative 2. When you multiply a number by a negative exponent, it's going to get smaller. We need to move the place value 2 places. So we have 6.3, 1, 2, and that's 0.063 times 10 to the, now remember the purpose was to change the exponent to 10 to the 7th. Then you can multiply both of these out to double check and make sure that they are equivalent. So that's 0.063 times 10 to the 7th. Next example, 8.1 times 10 to the negative 2. We want to change our order of magnitude to 10 to the negative 4. So we write 8.1 times 10 to the negative 4 times 10. This exponent and this exponent needs to add up to negative 2. So negative 4 plus 2 is negative 2. Now we want to preserve this base 10, so we multiply 8.1 times 10 squared. You move your decimal 2 places, and that's 8100 times 10 to the negative 4. 8100 times 10 to the negative 4. In our last example, we want to change our exponent from negative 12 to negative 10. So we have 2.4 times 10 to the negative 12 times, whoop, that should not be negative 12. Let's start that over. 2.4 times 10 to the negative 10. So that's our new exponent times 10 to the, now we know that these two exponents need to add up to negative 12. So this would be negative 2. We want to preserve 10 to the negative 10th. So we multiply 2.4 times 10 to the negative 2. That's going to make this number smaller by 2 place values. So we have 1, 2. So we have 0.024 times 10 to the negative 10th, and those are equivalent. So let's take a look at what happens when you are increasing your exponent. When you are going from 10 to the 3rd to 10 to the 4th, you are increasing this place value by 1. Then what happens to your decimal is that this needs to decrease by 1 place value. So you move your decimal 1 place to the left. Then let's take a look at what happens when you move your exponent, or you change your exponent twice. So here we're going from an exponent of 3 to an exponent of 5. So this one would be 1,000 and this would be 100,000. So our exponent is increasing by 2 place values. When you increase your exponent by 2 place values, you need to decrease your decimal place by 2 place values as well. So it goes from 8.7 to 0.087. Then let's take a look at the pattern with the negative exponents. We are going from a -7 to a -6. So we are increasing our place value by 1, which may be a little confusing because they're negative exponents. But remember, when you go from a smaller negative to from -7 to -6, you are actually increasing. So when you are increasing your exponent by 1 place, then you need to decrease your decimal by 1 place. Again, when you increase your exponent, you need to decrease your decimal, and that's going to move it 1 place to the left. And that's why it's at 0.62. So let's take a look at what happens when you change your exponent by 2 places. So we go from -7 to -5. We are increasing our exponent by 2 place values. That means you need to decrease your decimal by 2 place values. So you move it over 2 places. So summarizing, for each place value, your magnitude increases, which is this blue column. Then the other place value must decrease by the same. Add that to your notes. When your place value increases, your other place value decreases. So your decimal moves to the left. Now let's take a look at what happens when your exponent decreases. When your exponent decreases, so we're going from 7 to 6, it's going down 1 place value. When it goes down 1 place value, then your decimal must increase by 1 place value. What about if you're increasing it by 2 place values? So we're going from 7 to 5. Did I say increase? I meant decrease. So when we are decreasing our place value by 2, then our decimal needs to increase by 2. So our decimal moves 2 places. Then let's take a look at what happens when you're using negative exponents. So here we're going from -4 to -5. So we are decreasing our exponent by 1. When you decrease your exponent, then you have to increase your decimal by 1 place. Let's take a look at when you change it by 2. So here we're changing our order of magnitude from -4 to -6. So we are decreasing our exponent. Then you need to increase your decimal. So 2 place values here and then 2 place values here gives you 320. So let's summarize that. On the left side, for each place value your magnitude decreases, the other place value must increase by the same. So what happens to your decimal? When your exponent decreases, then your decimal moves to the right. So look at our arrows. When your exponent decreases, then your decimal moves to the right. When your magnitude increases, so this is your exponent, when your exponent increases, then your decimal moves to the left. Okay, so this is your exponent and this is your decimal. This is your exponent and this is your decimal. In this lesson, you have learned to write a number in scientific notation, to recognize if a number is written in scientific notation, to rewrite a number using a new order of magnitude, and to find the sum or difference of numbers written in scientific notation.